Hi, everyone. We are continuing day 3 of the second lesson, lesson 2, such a rad lesson. And we're on page 28. Let's see here, 2.3, the cube root function. So this is what we're supposed to do yesterday, but we didn't get to it. That's okay. We got to it today. And we have here the table, and you were supposed to graph this and then graph the inverse. So if you did not do that already, pause, do a thing. So if you notice here in purple, we have the regular function, the cubic function, which we have seen before. And the pink one, this is the inverse function. And if you notice there, I said inverse function. Is it true? Did I say it right? Or does it pass the vertical line test, right? So you take, looking at just the pink one, right? The pink function, do the vertical line test. Does it cross the vertical line more than once? No, doesn't. So that's why it is true. It is the vertical function. And so that's why we can write on here c -1. Do you see the c -1? So this is the inverse function of c. Okay, so there we have it. If you also note, another thing we talked about in class today was notice the points that are the same, right? You know, like remember in the parabola, there were a couple of points that were the same. Here we have 3. And the question is, well, why those 3? If you notice, it's these 3 right here. Well, if you notice, the x and the y are exactly the same. So if you flip them, same thing. And if you remember way back in lesson 1, maybe lesson 2, we talked about day 1, lesson 2. So there was a line instead of, you know, like what we did with the paper. Remember when we copied it down, or hopefully you did. And if you didn't, then you didn't, I guess. So remember when we rotated and then flipped it? So instead of doing that, the other way to do it is if you were to just draw a line straight like this and were to just flip it, you see how it looks exactly the same? So this line that we're talking about here, that is y is equal to x. So that's literally the equation, y equals x. So let me just see if I can draw it right here. Okay, so this is y is equal to x. And if you notice, if y is equal to x, that's literally, they're the same number, right? Notice the y-intercept 0, the slope is 1. So every 1 you go up, you go 1 to the right, right? So that's why it's always the same, x, y. All right, so, and that is your line of reflection. This is line of reflection. It's a good thing to think about. Line of reflection just right there. And notice those 3 points are on the line of reflection. Exactly, right? If you look right here, number 4, we talked about the domain and the range. For a cubic, they go this way, right? So we're going slightly to the left. For you, I guess that would be right. Should I do it this way? Slightly to the right and slightly to the left, which means if it's even slightly going to the left and right and they have arrows, means it goes on that way forever and ever, right? So it's from negative infinity to positive infinity for both the domain and the range. X and y intercepts, yep, at 0, 0. That's the only place where, that's the only point where it is both on the x-intercept, x-axis, and the y-axis. Only point, the origin. And so we got our zeros here and then our infinities here. And remember the inverse function, exactly the same thing but they're switched. So this range would go to that domain. However, since both the range and domain are the same, so that's why it looks like it's exactly the same. And then the x and y intercepts are the same, still at the origin. There we go. And these are what, so this pink part right here is what we call a cube function. I should say cube root function. So let me just highlight that, guys. So the cube root function, we know to be this guy right here. And why this is capital X, I'm not sure. I think that's a typo. It should be lowercase x. We usually use capital letters for geometry, like points and things. And okay, so that was that. And so the things that we've been doing so far, so with yesterday, with the domain restrictions, right, with the quadratics, that is going to be with the square roots. So the square root and the cube root, these are all radical functions. When I talk about radical functions, you're like, what are those? Is it really radical? This little symbol, you know, the square root symbol, that's called the radical symbol, okay? So the radical meaning, it could be a square root, it could be a cube root, it could be a 4th root, it could be a 5th root, anything like that. Anything above equal or above a 2. Okay, so that's what that's going to be. And these other things also have names too, but we're not gonna name names. And then we went into 2.4, which is inverse by composition. We call these composite functions. And so thus far, we've been able to see if a function was invertible by looking at its graph, right? You do the vertical line test and the horizontal line test, and if it passes both of those, then that function is invertible. And I said that we're going to be able to do it algebraically as well. Today's that day. Yay, we finally got to the day. So before we get into composite functions, right, the algebraic side of things, I'm going to take a look at over here. Originally, I had been like, oh, don't look at this. Okay, so pretend you didn't see that. Okay, don't rewind. Don't try to go back. It's cheating, right? Or if you were in class, I guess you would already know. So if we have f of pizza, so f of x is pizza, and g of x is pineapple, then what would, so we're going to just kind of combine these guys. So we're going to, inside of f of x, we're going to put in g of x. You see the coloring? So g of x is in the inside, and outside of it is f of x. So what are we putting inside? What is the x for f of x? It's the g of x. Okay, so what would that look like? So imagine you'd have your pizza, and what are you putting inside it? The pineapples. Agree or agree to disagree. It's up to you. I personally love pineapples with my pizza. Back when I could eat pizza. Now I can't eat pizza. It's sad days. Oh, I was supposed to show you. And then, so what if we reversed it, right? We have g of f of x. So we're going to take g and put f of x inside it. So what would that look like? So that would look like, if you were really quick, you knew or saw, you have a pineapple, and inside it, what do you have? Pizza. See, that's what that would look like. It's weird. Are these the same thing? So is f of g of x and g of f of x the same thing? No. Algebraically, is it always going to be the same thing? No. It may be the same thing, but not always. Okay, and so that's what that would look like. And the in one of my classes, I said, well, you could have, not only could you have functions within functions, but you could have functions within functions within functions within functions within functions. Like you could keep on, you could just do that for days, right? So what we would do, so if f of x is equal to pizza, and g of x is equal to pineapple, and h of x is equal to chocolate. Don't ask about chocolate. I don't know how that became to be. It just is, right? So what would that look like? So let me just erase this really quick, and let me just draw it in for you. So here we have h of g of h of x. That's how we say it. Every time you see a parentheses, you would say of. So h of g of h of x. So first I would draw this outside one. So this is like what sort of like framing, like we're going to frame this, right? So what do we have? We have the pizza. So here I'm going to draw the pizza. Okay, now we know where we are. So now we're inside of pizza, we're going to put in the g, which is pineapples. So we're going to put in pineapples. I should probably do like yellow, huh? We don't want like green pineapples. Okay, I guess we don't have purple pizza either, so. Okay, so here is the pineapples. Okay, imagine that they are pineapples. Very strange looking pineapples. And then we're gonna have chocolate. So, and I don't have, okay, this is brownish, bronze chocolate, okay? So then we have the h of x. So on top of, or inside of the g of x is h of x, right? So basically inside of on the chocolates, on the pineapples, we have chocolate. See? That's how this is gonna look like. Or if you want to think about, the Russian nesting dolls, where you have a doll inside a doll inside a doll, it's kind of like that, okay? So what we're gonna do here, if you take a look at on the left-hand side, we had an example. And in your class, it may have been different. I kind of use different examples for every single class, just because. And sorry, period 3, yours was a little bit more complicated. So I was like, I learned from that one. I was like, maybe I should make it that complicated. So here we have f of x equal to 2x plus 1, and g of x equal to negative 3x minus 5. I use these numbers because I feel like if you try it like this, it might make a little bit more sense when we get into the work example. So we're going to first try f of g of x. What is that going to look like? So inside of f, what are we going to put in g of x? So just like how we drew our pizza first, we're gonna like draw the F first. So it's gonna be 2 parentheses, and then that's gonna represent our X. So whatever is X, that's what we're gonna put in there, and then +1. So I try to color coordinate them. Do you see? Color coordinate, just like that. So instead of this X, I'm gonna put in what G of X is. So what is G of X? That is this guy right here. That is this, pink, come on. That is this -3x minus 5. That goes right in here. That's the X. So then once you set that up, now it's just like algebra, like we were used to, right? Now we're just going to simplify, right? So you're going to distribute. So distribute the 2 with the -3x minus 5. Remember, not with the 1, because the 1 is outside of the parentheses, right? So it's going to be 2 times -3x, which is -6x, 2 times -5, which is -10. And then right here, we get the second line right there. And notice that this +1, I just plop it down because I'm just distributing right now. Now we're going to simplify or combine like terms. So it's going to be -6x minus, and then -10 plus 1, which is going to be -9 or -9. All right. So now the same kind of thing goes. Now we're going to reverse it. So we're going to go, we'll take G, and then we'll put inside G, we're going to put an f of x, right? So we're doing that framework of G. G is -3x minus 5. Remember, instead of x, we're going to put in the parentheses. Okay, that's like my placeholder. Because what are we going to put inside there? The f of x. Okay, the f of x. So it's going to be 2x plus 1. All right. I cannot color coordinate these because that means I have to erase all that. I'm just not going to do that right now. So that's going to be what that is. And then again, we're just going to simplify. So we're going to distribute. So -3 times 2x is -6x. -3 times 1 is -3. And then drop that -5 down there because we haven't dealt with that yet. And then combine like terms. So notice here you get, when you have G of f of x, you get -6x minus 8. It's similar, but it's not the same, right? Kind of like these two in the pizza with the pineapple. It's similar, but it's definitely not the same. Like they have the same ingredients-ish, but it's not the same, right? Which one would you rather eat? Or maybe you don't want to eat either. But I will say, if you ever try pineapples with chocolate, you know, where's the chocolate fountain, and you just put that pineapple in there. So good. So good. I can't help it. So this is what we call composite functions, or in this book, they call it composition of functions. It sounds very like, oh, it's the composition of functions. But it's composite functions. It's the same thing. Composite meaning we're going to take two functions and put them together, kind of thing, right? And that's how we say that. Let's see here. Oh, and a little tidbit for those of you guys who, you know, just since you guys watch the video, you guys get a little bonus feature. Here's the bonus feature. So instead of saying like, because you know, if we say G of f of x, do you see how like this gets a little bit messy with a lot of parentheses, especially when you get to like 3, right? So you could write it. So G open circle f of x. You could do it this way. This also means composite function. So this is the same thing as this. It's the same. All right. So I don't know if you've seen this notation before. If you took geometry like 2 years ago or 3 years ago, maybe 3 years ago, then you may have seen this. Because when I was teaching geometry, we did me, Mr. Werfs, and somebody else. We taught it like that. But yeah, there is that way too. Let's see here. So okay. So now let's look at the worked example. I got sidetracked. I should stop. So here we go. So we're looking at, if we're saying that g of x is equal to x squared and f of x is equal to the square root of x. Of course, we have the domain restriction because we want to have it to be a function, right? Because if they're inverse functions, but if one of them is not even a function, we can't even function, right? So again, we have our domain restriction right here. That has to be stated. So what we're going to do, if you notice right here, they take the f of x. So they want to know what f of g of x is, right? So they're putting g of x inside of f of x. So they wrote down, I tried to color coordinate this. So we have the square root, and then they put inside, instead of x, they put in x squared. They put in what g of x was. So what is the square root of x squared? X, right? That's all we get, is x. Because the square and the square root, they cancel out, right? They're the inverses of each other, they cancel out. right? So yeah, that's equal to x. So then what you're supposed to do now is you do the opposite. So we're going to find g of f of x, right? Well, what is g of f of x? You take g, that's like your squared part, and then inside, what do you put in? F of x, which is a square root of x. So what is square root of x squared? What is that? And you'd be like, well, doesn't the square root and the square still cancel out? I'm like, yes, it still cancels out. So that's what all we have left is x. So if you notice, we got the same answer, which is x, both times, right? Coincidence? I think not, right? So, and here's the thing that you should highlight. I would write it out in big words or something like that if you do not have a book. So if f of g of x and g of f of x is equal to x, and it has to equal x, can't equal anything else. If it's equal to x, then f of x and g of x are inverse functions. Just like that. Okay, so they're inverse functions. Is that true for this case? Well, yes, we tried f of g of x, which was x, and g of f of x, which is still also x. So are they inverses? Yes, f of x and g of x are inverse functions because math. That's why I like this so much, because right here, that's the explanation. If you want to write that out in words, be my guest. I would say it will be a lot longer than writing that. Okay. And does it always have to be x? Yes, it always has to be x. And why is that? Why does it always have to equal up to x? Because remember, inverse functions, it basically undoes something, right? So if you think about this visual right here, I really like this visual. I didn't think of it. I think it's a great idea. So I stole this one. No steal. I borrowed this one. All right. So if your function is a stapler, so the inverse function would be the stapler remover. Okay. So because it undoes it, right? And I was like, that's genius. Too bad you can't flip it around, because if you have the stapler remover first and then staple it, that is it really? So maybe it just works only one way, but that is the general idea of it. It's not perfect. It's not a perfect example, but you get the idea, right? So basically, whatever function the g is doing, right? Whatever operations the g is doing, f is going to undo those, right? So that's going to undo those operations. So it should be the exact opposite. What do you have left? The only thing you have left, if all the operations are undone, right, is just x. You stripped it bare. Like, that's all we have left, right? All the operations have been canceled out. So that's all you have left is x. That's why. Okay. And honestly, finding these ones and doing them is actually quite satisfactory. There's a lot of satisfaction in it. I don't know why. I just like canceling things out. Like, nope, it's all x. All right. We don't have an example of that here. Unfortunately, it's not so complex. It's pretty simple. But if you look in the exit ticket, plug for my exit ticket, do the exit ticket, because there is an example of that in there. Or it's a little bit more complex than what we just did, because that's pretty simple. You can visually look and be like, yeah, they're the inverses. But there are some that it's kind of hard to tell. You're like, maybe they're inverses. So there we go. So the last part here for today is we have A and B. We have h of x and q of x. Are they inverses? So I would really like you to try these by yourself. If you did not do them already in class, if you missed class, or you couldn't hear, or you couldn't, whatever, XYZ thing, that's what I would do. All right, and then check your work here. The first one, you should get them to be simplified to be both x's, right? Because the cube root of x cubed is canceled out, those cube and the x cubed, cubed and the cube root is what I should say. So those cancel out, so you just get x. Same thing with vice versa, right? That also cancels out. So yeah, h of x and q of x are inverses of each other. If you look at B, the tricky part here is what to do with this guy right here. Most people in general could plug it in, right? So they could get to here, this first line. But then after that, there were some questions about what to do with them, right? So please make sure you do not multiply first. Because remember, order of operation, that is the cardinal rule, right? If you multiply first before you do the exponents, you're going to get in trouble. Like, this is not going to work out for you, right? Because it's not going to be good. So you could either do it one of two ways. So you could either do the distributive, which this is a little bit messy. So I'm sorry, you can write it out this way. me get back to my green color here. Nope, that wasn't green. I'm just kidding. That was just blue. So you could either write it this way. Do you see on the right-hand side how, remember this is squared because this says square. I color coordinated that. So you would just multiply it out this way. So you're going to do multiply 2x squared times 2x squared, and then multiply 2x squared times 5. Or you could either, and then don't forget the bottom part, you know, I always go beneath. Some people go above, but I feel like it's too messy. Or you could do the box method. Either way is okay. And you're like, oh, that's still a thing. I'm like, it's always a thing. Okay, so either one of those two, this is what I mean by distribute. Okay, because this is what we're doing, is just big time distributing. All right, so that's how you would get these answers right in here. And then just make sure you distribute afterwards, distribute the 2, and then add the 5 at the end. Okay, and these are the answers that you should get. And you're like, oh, these are so close. They're so close to being the same. Even if they were the same, would they be inverses? No, they would not be inverses. Why? Because they're, what does it have to equal to? It's equal to x, right? It has to simplify all the way down to be x, right? And so that's how you know that they're inverses. So that's what that's going to be. Yeah, these are not inverses. That's why here, not inverses. Although you can see from the very beginning, there was a student in class, in one of the classes, who said, yeah, they just looked at this and was like, nope, not going to be inverses. And how do I know that? Because they're both squares. They're not going to, like a square is not going to like be the inverse of another square. It's not going to undo another square. So if you see a square in one, then the other one should have a square root in it somewhere, right? I don't know where, but it should at least have a square root in it so that there is at least a chance of it canceling out, right? Just like how one of them has a plus and the other one has a minus. So that plus and the minus may cancel each other out, right? So that's a way to visually look at that and be like, ooh, yeah, this one's not going to have a chance. Like this one B, we could have been like, we could have saved all ourselves a lot of trouble and be like, yeah, no, those aren't functions. Or no, those are functions. They're not inverses because, you know, whatever it is. Yeah, they're definitely not going to do each other. All right. Oh, number 4. I guess we didn't talk about number 4, but we can. Mike said that all linear functions are inverses of themselves because f of x is equal to x and the inverse of g of x is x. Is Mike correct? All linear functions are inverses of themselves. So what I like to do is like, no, you're wrong because, you know, and you gotta have to like, well, what about this? You know, so you have to have some kind of counterexample, right? So let's say if f of x, oh no, let's make it, because he uses f of x here. So let's use like, let's use blue. M of x. Okay, so m of x is equal to, we say it's all linear functions, right? Let's go 2x plus 1 are inverses of themselves. Okay, so inverses of themselves. So let's try this out. So let's go m and p of x. So it has to be the same thing, right? So let's just try it out. So m of p of x, and if you can kind of see right now, it's not going to cancel out. Maybe you see it, maybe you don't. I should probably change this to a different color. See if we can do it. I will get there. So let's change that to green. And this guy right here is also going to be green. Okay, so I've color coordinated now. So p of x, so 2 times whatever this x is plus 1. And then I'm going to put instead of x, I'm going to put in 2x plus 1. And you can see, are we going to undo the multiplication? Yeah, no. So we're not going to be able to do that. This would just be 4x plus 2 plus 1, which is going to be 4x plus 3. So automatically, I don't even need to check the other one because you can see right here, not an inverse, right? This is my counterexample saying, no, Mike, I don't think you're right because m of x is a linear function and p of x is the same linear function, you know, because you said they're inverses of themselves, right? We're not doing any like finding the inverse or anything like that, right? So therefore, and we put one inside the other, right? Because if they are inverses, then they should simplify down to be just x, but it didn't. So here's my example to show you why it's not. So that's what I would say, right? And tomorrow, or not tomorrow, the next lesson, we're going to talk about a little bit more about these applications of when do we use this stuff, right? When do people even do this, right? Why is this useful? So that's what we're going to do. I will see you guys later. Bye.